Okay, this is kind of a practice quiz for a quiz we're going to be having coming up. And what we want to do is make sure that we are complete in our solutions. I put the point values down for everything that you're going to be dealing with. So if you want those points, you're going to have to, do the work, all right, and actually show what's going on. So first of all, we have this function number one. Now this first part was worth, I think, about 12 points if you add up all the little point values here. And the first thing we want to do is use analytic methods to find the exact intervals in which the function is increasing, decreasing, concave up, concave down. Now increasing, decreasing, this kind of implies the first derivative test. This implies the second derivative test. But just to make sure, I wanted you to apply the first and second derivative tests and use only the x values of the critical points in your statements. That way you won't have to go back and put the values into the function. So let's get to work here. So number one, of course, we're just going to try to find the relative extremas. That's when we're using the first derivative test. And I've got y equals, I guess I'll write this over here, it should be fine. Y equals 4x cubed minus 21x squared plus 30x plus 6, and I'm going to take the derivative and check for my increasing and decreasing. So that's going to be 12, 3 times 4 is 12x squared minus 42x plus 30. And again, if we're going to apply the first derivative test, and what you'll have to do now on your quiz is you'll have to draw these lines and then write these statements below. All right, make sure that that's clear to whoever's grading it. All right, so make sure you draw the lines and then write the statements below. And you just have to write everything here and then fill these in. So I pretty much outlined it, what I expect you to be able to do. Okay, so I think that's pretty fair. Okay, so we want to check our critical points, and y prime is not going to be undefined because it's a nice polynomial, so we won't have any issues there. But y prime will be equal to 0. So we set this equal to 0 and find out the values that will satisfy that. And those will be my critical numbers, or the x values of the critical points. So 12x squared minus 42x plus 30, so I set that equal to 0. Now this is a quadratic, and what we can do is we can divide. It's an equation now. It's not a function anymore. It's an equation. So I can get an equation that will have equivalent roots or zeros just by dividing through by some common number, and everything is divisible here by 6. So I'm going to divide every term by 6. And I'm going to get an equivalent function as far as the roots are concerned. So that's going to be 2x squared minus 7x plus 5 equals 0. Now this quadratic equation will have the same zeros as this quadratic equation. Now if I graph them, they're going to look a lot different. They'll both go through the same zeros. This will probably be a lot steeper. Okay, more like a V, or this might be more like a U. But they will have the same zeros though, so keep that in mind. That's all we're trying to do, is find the zeros. That's all we're interested in. So I'm going to have to factor this. So if we factor this, hopefully it will be factorable. And we need numbers. Well, this is nice because this tells me that these sides have both got to be the same, so both must be negative. So I know right away I've got negative signs. That's nice. And there's only one way to get 5. That's 5 and 1. So this is an easier one. So how am I going to do that? Well, I can put 5 here and 1 here and kind of try that. And that's going to be 1 minus 10. That's not going to work. That's going to be minus 11. So let me put the 5 here, because that's probably going to work, and the 1 here. Now please check these. So this is going to be 2x squared, and that's going to be positive 5. So the outside and inside, the outside or the left terms and the right terms work. Okay. Now let's do outside inside, and let's see, we have negative 5x and negative 2x, because negative 1 times 2 is negative 2, and negative 5 is negative 7, so that checks out. So my possible roots, or my roots are, not my possible roots are, I set this equal to 0, so 2x minus 5 equals 0. So 2x equals 5, x equals 5 over 2, or 2.5. And over here, this is easy, x equals 1. So those are my critical numbers. This is like 2.5. So those would be the numbers that go over here. 1 and 5/2, I guess. Okay, so those are my critical numbers, so those have to be in there. That's going to be one of the points and stuff. Now we have to check the SIGNs over here and see what's going on. So again, we can use this rather than actually putting these numbers in, which we could do. And over here, we'll be able to do that because we could try 0 here. And that's easy because if I put 0 into my derivative, now this is my derivative here, so this is what I want to check. It doesn't, but this is going to be equivalent to have the same SIGNs because it's reduced. So if I put 0 in here, I'm going to get positive, so that's nice. And then if I put like 2, this is 2 here, that's between, because this is 2.5. So if I put 2 in, I can either substitute 2 in here and see what sign I can get, or I could just check these. If I put 2 in here, I'm going to get a positive, so that factor will be positive. And if I put 2 in here, 2 times 2 is 4, minus 5 is negative, so I've got a negative times a positive, so that's going to make this negative. So that's another way to do it, rather than actually putting the numbers in. I could put 2 in here, but then I've got to work all that out. Or I could look at these two factors. And then I could try 3 over here. And if I put 3 in here, I get positive, and 2 times 3 is 6, minus 5 is positive, so I get a positive times a positive, that's also positive. So now I've got what's happening here, okay? All right, so we talked about these little arrows we can use, and this is basically is positive, so that means my slope is positive, my derivative is positive, so my function is increasing, decreasing, and increasing, so there you go. All right. Okay, so it looks like we have a relative minimum at x equals 5/2. Okay, because y prime changes from negative to positive there. Okay. And it looks like we have a relative maximum at x equals 1 because y prime changes from positive to negative there. So you got to write this to get your points because this is worth 1 point, this is worth 1 point. And it's mostly the statement because you should have these on your line. Okay? And then we know it's increasing here and here. Now it's going from negative infinity. So that's always a... And then since it's positive in this interval, we say it's increasing on the closed interval, so that's going to be to 1. And then it's also increasing from 5/2 to infinity, and infinity is always open. Okay? Because the derivative, remember, if the derivative is positive, we say the function is increasing on those intervals. Since the derivative is negative, we say it's decreasing on this interval, and that's going to be closed. 1 to 5 over 2. Okay? So that's so there's your 1, 2, 3 points. Okay? And this might be 1 point for the top and 1 point for the bottom, 1 point for this statement, 1 point for that statement. Okay? And now we want to check the concavity and find the point of inflection. So let's take a look at this. So we'll take the second derivative, so we can go back over here. We could start here as the first derivative, so y double prime equals 24x minus 42. And again, that's not going to be undefined, but it is going to be equal to 0, so I can say 24x minus 42 equals 0, and then I could divide by 6, because 6 goes into each of these. That would be make it a little bit easier. And I get 4x minus 7 equals 0, so 4x equals 7, so x equals 7 over 4. Okay, so that's going to be a possible point of inflection. Hope you can see all that. Sorry about that. Okay, so we set the second derivative equal to 0, and we get 7 over 4. So that go over here. So is that a point of inflection? Well, we have to check and see if it changes signs, and it's pretty easy. We could try 0 is a good number because that's less than 7 over 4. And we could try 2 because that's greater than 7 over 4. And if I try 0, I'm going to get negative. That's not okay. And then if I try 2, that's positive because 4 times 2 is 8 minus 7 is 1, so that's positive. So I do have a change of concavity. Now, since this is negative, this is going to be concave down. And since this is positive, this is going to be concave up. And you see how that conforms with what we're talking about over here. Because 7/4, 1 3/4 is kind of like over here, so you can see what's happening. See, it's concave down, so my point of inflection is right over here. All right, so we say we have a point of inflection at 7/4. Why? Because concavity. Concavity changes. There. Okay, and then here we can just use open intervals. We say it's concave up from 7/4 to infinity. And it's concave down from negative infinity to 7/4. Okay, and there you go. So that's the whole shebang. You need to be able to write this out, so practice this, and I hope it all makes sense. And I'll do the second one in just a moment.